A rhombus ABCD is formed of four uniform rods, each of length 2L and weight W, freely jointed at the corners. A light inextensible string also of length 2L joins A and C. The system hangs in equilibrium from two vertical strings attached to points A and B, with rod AB horizontal. Find the tension in each of the three strings. So the strings are shown here in green. We will start by considering the forces acting on this rod here. Well, the weight of this rod is W, we can put this weight factor at the center of gravity, which is the midpoint of the rod since the rod is uniform. Now, what about the forces at point D? Well, we want to consider the force on rod DC due to rod AB. Now, we don't know what direction that force is in, but let's just indicate the vertical and horizontal components. Again, at the moment we don't know the direction of the vertical or horizontal components. Let's suppose that the vertical component is upwards. Let's say its magnitude is P. Let's suppose that the horizontal component is pointing to the left and its magnitude is R. Now let's consider the moments of these forces about the point C, so we don't have to worry about the forces on the rod at the point C, because their moment is 0, since C is on the line of action of those forces. Now straight away we can see that P must indeed point upwards. If we had it pointing in the other direction, then we would not have equilibrium. P was pointing this way. Obviously we would have a moment, an anti-clockwise moment about the point C. Okay, so straight away we can see that P was indeed pointing in the correct direction. What about the moment of P about the point C? Well, we multiply its magnitude, which is P, times the perpendicular distance of C to its line of action, which is 2L. And that's the only force that has a clockwise moment about the point C. R has no moment about the point C. So even if R is pointing to the left or pointing to the right, it doesn't matter. Its line of action contains the point C, so its moment about C is 0. W has an anti-clockwise moment about the point C, so we multiply W by its distance from C, which is actually L. It's half of the length of the rod, half of 2L. So straight away we can see that P is a half W, and we know its direction. It's pointing vertically upwards. Now let's look at the forces on the rod AD. Well, we have its weight, which acts at the center of gravity. Now what about the force on rod AD due to rod DC? Well, we apply Newton's third law. Okay, the upward component of the force on DC due to AD is half W. So we have an equal and opposite component acting on rod AD. And we also reverse the direction of R. Okay, so we have just applied Newton's third law to get the contact force on the rod AD due to the rod DC. Okay, so the contact force on DC due to AD is this force here, if we sum these two, and by Newton's third law the contact force on AD due to DC is equal but opposite. It's this force here, but we will just show the components, and we'll remove these now because we're not interested in the forces on DC at the moment. Let's consider the moments of these forces about the point A, so we don't have to worry about the forces on the rod AD at the point A, because their moments will be 0 about the point A. Now, notice something interesting here. These three forces all have anti-clockwise moments about the point A, so they don't sum to 0. But they must sum to 0 for equilibrium. So there's something wrong here. Well, obviously the direction of R must be wrong, so we need to switch its direction. So here is the force on bar our rod AD. So that means that for the other rod, R must have been pointing in this direction. Okay, we will get back to this rod soon enough. I just want to continue with analyzing the forces on rod AD. Okay, so let's look at the clockwise moments. Well, those are W and a half W. So how do we get the moment of W about point A? Well, we have to get the perpendicular distance of the line of action of W to point A. So what is that distance? So we need some angles. Well, if we look at the geometry here, we have an equilateral triangle. So this angle is 60 degrees. Same as this one, and the same as this one. 3 equal sides, 3 equal angles. So this angle in here is also 60 degrees. These are a pair of Z angles. So we want the side adjacent to 60 degrees in this right angle triangle here. So 2L is the distance from here to here. So the distance from here to here must be half of that, which is L. So we multiply, to get the side adjacent to 60, we multiply L by cos 60. So the moment of W about the point A is W times L cos 60. It's a clockwise moment. What about a half W? Well, we multiply its magnitude, which is a half W, times the perpendicular distance of its line of action to A. Well, that's just twice L cos 60. Okay, we have to, you know, we have this, this triangle is congruent to this triangle, basically. So we have a half W times 2L cos 60. Okay, so those are the clockwise moments of the forces about A. So the sum of the clockwise moments, or I should say the sum of the magnitude of the clockwise moments, is equal to the sum of the magnitudes of the anti-clockwise moments. So here's vector R. So what is the perpendicular distance of the line of action of R to this point? Well, we need this distance here. Well, that's the side opposite 60 degrees in this big right angle triangle. So we multiply the hypotenuse 2L by sine 60. So we have R times 2L sine of 60. So we can divide all of this equation by L. Cos of 60 is a half. The 2's cancel here. We have another half W. The sine of 60 is root 3 over 2. So root 3 over 2 by 2 is root 3. So we get root 3R. So now we have found R in terms of W. R is W divided by root 3. Now, let's consider the part of the system that's indicated here in this color, whatever this color is, lavender, whatever. So this part of the system consists of 2 rods, and we are going to take moments about the point B for the forces on this part of the system. So we have the weight of this rod here. Now what about the contact force at this point due to the blue rod? Well, we just reverse the direction of these vectors. So here's vector R, whose magnitude we now know. It's W over root 3. Okay, so that's just applying Newton's third law. So we just reverse the direction of this vector to get W over root 3 pointing to the right, and a half W points vertically up. Okay, so this vector here is the force on the blue rod due to the lavender rod. By Newton's third law, the force on the lavender rod due to the blue rod is this vector here, the sum of these two components. So that's just Newton's third law. Now what about the forces at C? Well, the string is attached to the, well, one of the rods anyway, at the point C. So let's call this force T. We also have the weight of rod BC. So let's start with clockwise moments of forces on this part of the system about B. So what forces have clockwise moments? Well, this force has, it's x to turn the system clockwise about the point B. So we want the perpendicular distance of B to the line of action of this force. So just clear some of this. So we want a distance from B to this line of action, or we can go along this way. It's easier to see what's going on maybe. So the distance from here to here is L. What about the distance from here to here? Okay, let's fill in some angles. This is an equilateral triangle, so this angle is 60 degrees. We have another equilateral triangle here. See, these 3 sides are the same, so the 3 angles are 60 degrees. 60 and 60 is 120, so this one must be 60 to give 180. So we multiply 2L by cos 60 to get this distance. So we have to add L onto 2L cos 60 and multiply by W to get the moment of this force about B. So that's L plus 2L cos 60. Now, now this force here, W over root 3, also has a clockwise moment about the point B. It acts to turn the system clockwise about the point B. Well, it doesn't actually turn it, but you know, if it was by itself, it would turn the system clockwise about point B. Okay, so its magnitude is W over root 3, obviously, and we want the perpendicular distance of its line of action to be. So that's actually this distance here. Okay, so if we can, this is the line of action of it. So what is this distance? Well, it's the side opposite 60 in this right angle triangle, so it's hypotenuse 2L times sine 60. By the way, these are the anti-clockwise moments, not the clockwise moments. Now let's look at the clockwise moments. So the half W force has a clockwise moment about the point B. So what is the perpendicular distance of half W to the point B? So here's the line of action of a half W. So we need the distance of B to the line of action, which is the same as the distance of here to here. Well, from here to here it's 2L, and then we add on 2L cos 60. So we get 2L plus 2L cos 60. By the way, I need to go back here. I've left out an anti-clockwise moment. This force W has an anti-clockwise moment about the point B. So we need the distance of B to its line of action. What's this distance here? Well, it's just half of this distance. Half of 2L cos 60. That's L cos 60. So we have W times L cos 60. Okay, we go back to the clockwise moments now. The only other force that has a clockwise moment about B is T. So here's the line of action of T, and we want the perpendicular distance of it to the point B. So how do we get that distance? Well, we have a right angle triangle here, so we multiply the hypotenuse 2L by the sine of 60. So we get T times 2L sine 60. Now we equate these, of course. We divide across by L, so we get W times 1 plus W times 2 cos 60. Cos of 60 is a half, so we get we just get 1 here. So we have W times 2. Okay, we get these two W's. Then we have sine 60 is root 3 over 2, so we end up with just W here. That's this term. Cos of 60 is a half, so we end up with a half W here. On the right hand side, 2's cancel out here, so we have W plus W cos 60. So we have W plus a half W. And sine 60 is root 3 over 2. So the 2's cancel out, we get root 3 times T. So we get 2W equals root 3 times T, or T equals 2W over root 3. So that's the tension in this particular string. Now let's consider the tensions in these two strings. Now what I will do is I will replace the system, which consists of 4 rods, with its center of gravity. So the center of gravity is a point, so we can pretend that the mass of the system, which is actually 4W, 4 rods of each of weight W, is concentrated at the center of gravity. Now the weight of the string is of course negligible. We are given that the string is light. Where is the center of gravity? Well, a rhombus is a regular shape. It's a parallelogram, and the balance point of a parallelogram is where the diagonals intersect. Okay, see, if we draw in this diagonal, we get two congruent triangles, so it's easy enough to see that the center of gravity, or the balance point, if we were to place place a pin here. Well, if there's a uniform lamina, we could place a pin at this point and balance the rhombus. It's the same kind of idea. Well, it's not a uniform lamina, but the rods are uniform. So this would be the balance point. Okay, so we can pretend that the mass of the entire system, 4W, is concentrated at this point. Well, I should say the weight of the entire system is at this point. If we want the mass, we would of course divide the weight by 9.8. So I'm showing the external forces on the system. Okay, so for equilibrium, of course, the resultant force must be 0. So forces up, R plus S, must equal the forces down, which is 4W. Okay, these forces have no horizontal components, so this is just showing that the resultant force is 0. Now, for equilibrium, we need to use the fact that the turning effect of these forces about any point must be 0. So let's get the moment of these forces about a point. Let's get the moments of these three forces about the point A. Well, B has an anti-clockwise moment about the point A. Its magnitude is given by S times 2L, and that's the only force with an anti-clockwise moment about the point A. R has no moment about the point A because the line of action of R passes through the point A. What about this force here? Well, this has a clockwise moment. So sum of anti-clockwise moments equals sum of the magnitude of the clockwise moments. Alright, so we have to take 4W and multiply by the perpendicular distance of A to the line of action of the 4W force. So what is this distance? Well, let's work from the right hand side actually. This distance here is 2L times the cos of 60, and we have to add on this distance. Alright, so well, actually it's a bit easier if we consider this line here that bisects. This is meant to be a vertical line. We know that the distance from here to here is L. So the distance from here to here is half of L. Okay. Because this point is on the midpoint of the side of the equilateral triangle. So this distance is L, half the side of the equilateral triangle from here to here. So we want half of that distance. So solving this, we find that S is equal to W. Now that we know that S is W, we can just plug into this equation, so we can see that R is equal to 4W minus S, where S is W. So R is equal to 3W.